Welcome back to Computer Science 3200. Today we are talking about one of the coolest things in all of AI to me, which is MiniMax and AlphaBeta. My life was literally changed by this algorithm. I don't think it will change your life necessarily, but I remember back in my undergrad, I took the AI course. It was a different course back then. And I implemented, this was a grad course. And I implemented the MiniMax and AlphaBeta algorithm for a game called Atax, ATAXX. And it's a board game that shares properties with like Othello or Reversi, but it's not quite the same. And I took a course with Michael Burrow at the University of Alberta, and this was during my PhD, and I was supposed to be there to do robotics, right, for my PhD work. Then I did this course with Michael Burrow, and I did this assignment in which I created an artificial intelligence using MiniMax and AlphaBeta that was able to beat myself at a game. And that was this like turning point in my life where I was like, wow, this is actually really cool. I can create something that's better than me at something. And I ended up switching my PhD to game AI instead of robotics. And here I am now teaching game AI. So you may not have this sort of same life epiphany as I did, but there's two parts of your life for me. One is like before you implement MiniMax, and then there's after you implement MiniMax, because it's a very powerful algorithm. So let's stop with the philosophy and the life stories, and let's get right into it. Okay, so today we're going to be talking about two-player games, MiniMax search, AlphaBeta pruning, and then assignment 3. So if you're watching this on the day that it has been released, then your assignment 2 is due tonight, and tomorrow morning assignment 3 will be available. Assignment 3 will be far less work than assignment 2. However, it still may be difficult to debug, so please start it early if possible. Okay, so let's get into the lecture. Let me get my laser pointer up here. Here we go. So multiplayer games. So far in this course, we've only looked at problems with a single agent. We did single agent search. So we did breadth first search, depth first search, A*. All of those are single agent search algorithms. Heuristic search can also be applied to environments with multiple agents or multiple players. And remember way back in like the second lecture, we talked about the different properties that we can have for an environment. So we talked about like fully versus partially observable, deterministic versus stochastic, dynamic versus static. If you forgot about those things, you should go remind yourselves about those things because they will be on the exam. However, another important game property is the number of players in the game. So how many players are there in the game? For example, if we're talking about like traditional board games like chess or Go, we could have 2 players in the game. In baseball, there are 18 players, 2 teams of 9 players each. In StarCraft, we could have 1 versus 1, 2 versus 2, 8-person free-for-all. In poker, we could have 10 people. In Among Us, we could have 12 people. In one of these battle royale games, we could have 64 people all trying to kill each other, right? So games can have vastly different setups in terms of how many players are in the game and how they interact with each other. So in the game theory section, which were the last 2 lectures, we talked about payoffs. So what does each player hope to achieve in this game? Well, we talked about some different examples. We talked about the prisoner's dilemma, where we want to maximize our reward. In poker, we might want to maximize our profits. In chess, we might want to just win the game. So there's this concept of a zero-sum game, and a zero-sum game means that each player's gain or loss of payoff or utility is equally balanced by the utility of other players. So win-loss games are zero-sum. So traditional board games are 2-player, zero-sum, alternating move, perfect information, deterministic, and discrete. Okay? So these are the properties that will allow us to very easily apply the MiniMax search algorithm to these games. So who here has heard of Deep Blue? It was kind of the AlphaGo before AlphaGo. So back in 1997, Deep Blue, which was this huge cabinet here, played against the world champion Garry Kasparov at the game of chess. And it was the first time ever that a computer beat a world champion at chess. And it sort of ushered in this era of computer dominance over humans at traditional board games. So if we want to make something like Deep Blue, how can we design an algorithm to play a 2-player alternating move game like chess or like Go, etc.? So one thing we could think of is, first, maybe let's do some analysis of the game, and we could do some strategy or tactics or something. So for example, maybe we're going to say something like, okay, the queen is a really important piece, so maybe I should try my best to take the queen. So maybe you'd write a little algorithm that like found the queen of the opponent on the chessboard and tried to go for it or something like that. However, that can get you sort of like a decent little AI that knows how to play the game and does something, a little bit dumb but a little bit smart. So what if we take it one step forward and we take that and we just like make thousands of if-then statements, right? So if their piece is over here and this piece is over there, then they're doing a Sicilian strategy or something like that. So if they do a Sicilian strategy, then we have to counter with the Gander strategy, and then the Deer Lake strategy kind of counters that, right? So there's all these different if-then statements you could make, and that can also get you like a decent AI, but you don't really want to go down that road when you're thinking about AI algorithms, because you want an algorithm to not necessarily contain all of this hard-coded strategy, because ideally the same algorithm that plays chess should be able to play checkers, right? If it's a decent algorithm. So let's look at trying actions. So we're going to call this look ahead and evaluate. So what is look ahead and evaluate? This is one possible strategy that we could use. So here we have our game tree, okay? And so the game tree is going to be very similar to the search tree from previous slides, all right? So what we're going to do is we're going to have a current state up here. So this might be like the starting state of a chessboard, for example. And then these these edges are going to be different actions that I could take in the game. So for example, maybe like rook to A1. Now that's not a valid move, but this is like you move it to A1 or you move it to A3 or you move it to B4 or whatever. These edges are actions that you can do in the game, and then these nodes down here, they represent the resulting states after you've made that move. Okay? So you're taking moves on a chessboard or on a checkers board or in a Go board, just like you would have taken moves in a single agent game in the A-star search. So you're going to generate a list of actions from a given state, and these here are the actions that you can do. You're going to evaluate those actions based on the features of the resulting state. So for example, here, maybe I've got some function which returns, I don't know, this state is 8 good, or this state is 12 good, or this state is infinity good, right? So maybe I want to take this action. And then we're going to take the action which has the highest evaluation, right? So basically what we're going to do in this idea is we're going to check all the possible moves that I could do the moves, evaluate those states somehow, and then pick the one that had the highest value. Pretty simple. So here's the function. Here's a sort of a pseudocode for look ahead and evaluate. All right, so we've got our function definition. This is just going to take in a state of the game. Since we're trying to maximize something, I'm going to have this max val set to -infinity. And the reason it's set to -infinity is because as I go, I want to check to see if the current evaluation is bigger than the previous evaluation. So I'm going to set that initially to -infinity. And I want to also record which action gave me the best evaluation. So I've just set up an initial best action here equal to null. So the algorithm is really simple. It just says for every action in state.getLegalAction, so whatever our game is, it will be able to, we'll be able to get a list of all the legal actions that we can do. Then we're going to construct a child state. Okay, so this is going to be the child state. And we're just going to say state.doAction, action. Right? So we take for each action, we're going to create a new child, which is the result of doing that action on the state. So this doAction function here, that would apply the game rules of whatever game that this state represents, right? So for example, if this action was like moving a queen to take a piece, then the state.doAction function, if it was chess, would have all the logic for updating the board and removing the pieces, etc. Once we've generated this child, we're going to evaluate that child somehow. Okay, so this evaluation could take on a number of different forms. So who out there has ever heard of when you're playing chess that the pieces on the board are like worth a specific amount, right? So for example, some formulas out there have like the chess queen being worth 9 points, the pawn being worth 1, the rooks being worth 5, and knight is worth 3, something like that, right? So a possible evaluation for a chessboard might be just take the sum of all the point values of all the pieces that you have on the board, right? So if the sum of all the point values for your pieces is greater than the sum of all the point values for the opponent pieces, then maybe, just maybe, you're winning, right? So if you have more stuff, that's a decent evaluation. Now, obviously in chess, you can think of like, you're still able to checkmate the person if you have fewer pieces, but as a guess of the value of the state, that might be a decent evaluation function. So what we do is we apply some evaluation function to the child state after having done the action, and we record that. And then we say, if that value from that evaluation of this action is greater than my previous maximum value, then I'm going to set that maximum value. I'm going to record it. I'm also going to record that this action is the best action that I've seen so far. And then after I've done that for all the actions, I just return the best action. Okay? So, in a simpler example, this might be for tic-tac-toe. Let's say we have this current board up here, and it's X's turn to move, right? So I'm going to go look at the legal actions that I have. So the legal actions here is I could put a piece here, I could put a piece here, or I could put a piece here, right? So those are my 3 legal actions. So down here, look, okay, well, if I put a piece in the middle, well, then I win the game. So that's going to have a high evaluation. If I put a piece up here, that might have some other evaluation, and a piece over here might be even a lower evaluation. So what I would do for look ahead and evaluate is say, oh, look, I've won the game if I do this. So do that move. Okay. However, we can see very quickly that this is only looking one move in advance. So if we can't like see the end of the game from that one move, that's pretty bad. So what we want to do instead of just looking ahead one depth is let's try to search the entire game tree. Okay? So the game tree, remember, is going to be me doing a move, then you doing a move, then me, then you, then me, then you. But how big is the game tree? We talked about this a little bit beforehand, but to measure the size of the game tree, we have to know the number of actions that are on average from each state. So this is called the branching factor. So if I have 3 actions at each state, I branch out at 3, then 3 from each of those, then 3 from each of those, etc. And the game is going to end after some number of moves, so that's going to be the search depth. So the game tree is going to have size b to the power of d. I need to fix one slide really quickly. Give me a second. So our search tree is of size b to the power of d. And so if we recall our state and action space evaluation of a domain, the state space is the number of possible configurations for a given problem or a given game, right? And the action space is the number of actions that are possible from a state. And we use these as an estimation of complexity for the game. So we saw this before, but for tic-tac-toe, essentially, we have 3 possible values at each place on the board, right? Because it could be an X, an O, or blank. So for each of the spots on the board, it's one of those 3 things. So it's 3 to the power of 9 possible states, which is about 10 to the power of 4, or about 10,000, right? So it's not that big. We can easily search 10,000 nodes in like a millisecond, right? So tic-tac-toe is trivially solvable by these algorithms. However, for something like chess, well, we looked at this formula before. We have a bunch of places on the board. We have empty board spaces. We have a different number of pawns and a different number of pieces. And so if we do this calculation out, we have a absolutely gigantic number, okay? So there's 10 to the 43 possible states in chess, and we can't possibly search over all of those. And for Go, it's just way bigger. So let me just show you. So for chess, it's about 10 to the 43. For Go, it's 10 to the 172. So we can't possibly search those in our lifetimes. But this is only the state space complexity. There's also the game tree complexity. So there are far more possible game trees than there are states, because a game tree complexity measures how many different ways there are to achieve each possible state. How many possible sequences of actions are there in a game? And so we can't search the entire game tree. It's just not feasible for interesting games. We could do it for tic-tac-toe, but we can't do it for like any reasonable game. So what we're going to do is we're going to look ahead as far as possible. So whatever amount of time that we have, that's how far we're going to look ahead. So instead of searching the entire game tree, we're just going to search as much of the game tree as we possibly can. Okay? So this is what that might look like. Maybe you can search 10 nodes. Maybe you can search 10 million nodes. Maybe you can search 10 trillion nodes. I don't know how fast your computer is. But we probably can't search 10 to the power of 72 nodes, right? Okay. So we've seen a search tree before, but now what we have is a game tree search. And this game tree search, you can see here that I've colored it in different ways. Because what's going to happen in our game tree is that, at least for traditional board games, turn-based games, this blue player, let's just say that the blue player is the first person to move in the game. When the blue player takes their action right here, then it's red's turn to move, right? So if you're talking about chess, then you can think of this as the person who's playing the black pieces versus the person who's playing the white pieces. So white moves first in chess, followed by the black player, followed by the white player, followed by the black player, followed by the white player, etc. So it's alternating moves. So at each depth of the tree, you're going to alternate who is actually taking those moves. So, but at some point, we're going to reach as far as we can search in the tree, right? Here I've just made it depth 3, or depth 2, sorry. So at depth 2, if that's as far as we can search, then what we're going to do is we're going to apply our evaluation function. So here what I've done is I've gotten some leaf nodes down here, and these leaf nodes just contain random numbers that are going to be representing our evaluation of the states of the game at those leaf nodes of the search. So, how are we going to take these values and turn that into a selection of an action up here somehow? All right, well, let's look at this. So, let's say that I am trying to figure out which move that I should do. So I am this player, okay? I am trying to look at all of my actions, and I am trying to maximize the value that I get from any of these actions. Now, so I'm trying to maximize over these values right here. However, the opponent is trying to minimize those values, right? So if this evaluation down here, if a 6, so these values are listed with respect to my evaluation, right? So a 6 is better for me than a 2. An 8 is better for me than a 1. So the other player is going to try and minimize the outcome, and I am going to try and maximize the outcome. So let's just look at how this is going to work. The min player here, this is going to be a depth first search, okay? So we're going to come down here, and the first time we see an evaluation node, we're going to apply either min or max. So what this player has done is we see, okay, now there's these two nodes, right? I've reached the depth. So this is a terminal node in the game, and I've evaluated that terminal node. And so the min player is going to say, okay, which of these do I want to do, right? Well, if a 6 is better for my opponent, then I'm going to choose the 2. So this player is minimizing those two values, okay, and picking a 2. Similarly, on the other side, the player is going to choose the 1 instead of the 8, okay? And so now what I've done is, now that I've considered what my opponents can do, right? I've said if I was the opponent, I'm going to minimize these things. Now I'm going to look at the two values that they returned, and I'm going to choose the maximum of those two values, okay? So we've got a minimizing player, and we've got a maximizing player at alternating depths within this tree. And this tree could be much, much bigger. However, this is just like an easy example for you to understand. So before we had look ahead and evaluate. Look ahead and evaluate just did one depth, right? So it just looked ahead one depth. How are we going to extend the idea of look ahead and evaluate to do this sort of minimizing and maximizing in a recursive sort of way? Well, here's how we're going to do it. Let's turn look ahead and evaluate into a function called max value. Okay? So I've taken this and I've shortened it so that it'll fit on the screen. So here's the new form of look ahead and evaluate. It's called max value for a single depth. Okay? So this function max value is going to, just like before where we had max val equals negative infinity, now what we have is we just have v equals negative infinity. Okay, so that's the previous max value. Then, instead of going through and saying for each action, make a child and do the action, what I've just said here is I've shortened that to say for each child in the children of S. Okay, so that's pretty straightforward. Then I've got this v prime. V prime is just a new value that is the evaluation of the child, okay? So here I said val equals eval child. That is the same line as line number 4 here. And before, where I said if val greater than max val equals val, blah, 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 here I've just said if v prime, which is the new value, is greater than the previous max value, then set v equal to v prime. And then return the value. Okay? So this is the exact same algorithm as this, it's just much shorter, and I've shortened the variable names. And you'll see why in the upcoming slides. So this is the max value, right? So let's go back to this tree. So max value is looking over the two values here and trying to choose a value from that. But as we saw, if we don't have a terminal node there, we actually want to call the minimizing players function here, right? So we're going to call the max val of the min val. So what we do here is we're going to change max value so that instead of just calling evaluate right away, if it's not a terminal node, we're going to call min val, all right? So this is what that looks like. So now max value says, okay, if it's a terminal node, meaning it's either as far as we can search, or there's no more, like it's the end of the game, then we're going to return the evaluation of that state. Otherwise, if this is not a terminal state, I'm going to call min value, right? So see how that worked in the tree here? So max value, the maximizing player is going to look at this state, or this node. It was not a terminal node. So instead of trying to evaluate this node, it's going to call the min player. And then the min player is going to look ahead and say, oh, that is a terminal node. All right. So max value is going to call min value. So where's the min value function? Well, the min value function is over here. Okay. So max value is just what we just saw. It's going to call min value, and min value is going to call max value. So we've got one function which maximizes things, one function which minimizes things. It's going to keep going down and down and down in the tree, depth first search, okay, until it reaches a terminal node. If it reaches a terminal node, it's going to evaluate it, and then it's going to propagate that value back up the tree. Now, I do have a visualization of this coming up, so it makes it a little bit easier. And just remember that eval s is always going to return the score with respect to the maximizing player, okay? So now what we can do is this is the algorithm for the full tree, okay? So this will go all the way to the end of the game, which we just showed that we can't do because there's so much computation here that we could never possibly reach the end of the tree. So what we're going to do, just like we did with iterative deepening depth first search, we had something called depth limited search. What we're going to do here is we're going to introduce a depth limit. And the depth limit is just going to say, we've chosen some limit of computation that we're going to do, and we're going to stop the search and evaluate after we've reached that depth, because we can't search the entire tree. So max value and min value, they are going to just have one other parameter. You can see the differences between the algorithms here, okay? Where there's going to be another parameter called d, and that's the current depth of the search. So at the beginning, it's going to be 0 because it's the root node. And at the first level, it's going to be 1, then it's going to be 2, then it's going to be 3. So what we do is we say, if it's a terminal node or the current depth is greater than some maximum depth that we've chosen. Okay, so this maximum depth, that's going to be chosen somehow. We haven't talked about that yet. But it's just going to say, okay, if we reach the end of the game or we've reached our depth limit, that's when we evaluate. Then, when we call min value, we're going to take d and pass in d plus 1, right? And min value is going to do the same thing. It's going to pass into max value d plus 1. So here we have max value as a function, which calls min value. And we have min value, which calls max value. So what we're going to do now is instead of having two separate functions, I'm going to put all of this logic into a single function and separate the minimizing and the maximizing with an if statement. Okay? So this is the MiniMax algorithm. Minimizing, maximizing, MiniMax. All right. So the MiniMax algorithm is going to take as a parameter, or as parameters, the state that we're working on, the current depth of the search, and then max. So max is going to be a Boolean variable, which tells us whether or not we are currently trying to maximize or we're currently trying to minimize. All right? So this algorithm starts the same as the other two. So it's going to say if it's a terminal state, so if it's the end of the game, or the depth is greater than the max depth, stop. Okay, so we've gotten some depth limit that we don't want to do any more computation, so we evaluate there. Then, instead of having these two separate algorithms, we're going to say if we're maximizing, do the maximizing part. Otherwise, we're not maximizing, so we're minimizing, so do the minimizing part. Okay? So it just says if we're maximizing, set v equal to minus infinity for each child, and then instead of an if statement here, I just have a max function, right? So v is equal to max, v, minimax, child, depth plus 1, false. So if we're maximizing, the next time we call this function recursively, we want to be minimizing. So we'll pass in false for the maximization Boolean, okay? Otherwise, we do the opposite, which is to minimize it. And then when we call MiniMax again from the minimizing portion of MiniMax, we're going to call true because we want to be maximizing at that point. So that's it. That's the MiniMax algorithm. It's pretty intuitive. And I'm just going to put this here without explaining it too much, but there is an algorithm called Negamax. Nega here means negation, and there's a property of minimizing and maximizing, which is the maximum of A and B is equal to the negative maximum of negative A and negative B. So if you take that into account, you can actually shorten the MiniMax algorithm to this. I am not going to be asking about this on the exam, and I'm not going to be requiring that you implement this on your assignment, nor do I recommend it because it's quite difficult to debug. You do actually kind of want these if statements when you're going to debug this algorithm. But I just wanted to show it to you because I'm sure the bunch of people out there are going to be Googling MiniMax and stuff, and you may run across this form of the MiniMax algorithm, which is called the Negamax algorithm. But do not implement this for your assignment, okay? I just wanted to show you that it exists. All right. So properties of MiniMax. MiniMax is complete and optimal. It will find the optimal solution to a given maximum depth, okay? Each player plays a best response to the possible actions of the other player. So what does that mean? Someone in the chat who's paying attention, who's still awake, tell me, if each player is playing a best response to the possible actions of the other player, because one person is trying to maximize, the other person minimizes, then maximizes, minimizes, right? So these are best responses. So what is that saying? What is the MiniMax algorithm actually computing? We did this in the last lecture. There's a big hint. If each player is playing a best response to the actions of the other player, what are we computing? You got an exam coming up. All right. Well, we had one correct answer. MiniMax approximates the Nash equilibrium, right? Because remember, the Nash equilibrium is where both players are best responding to each other. Neither player can deviate or can gain by changing, and neither player has any regrets. And there's a property, and I'm not going to go into the proof of this, that for a two-player, finite, zero-sum game, a Nash equilibrium exists. And MiniMax is calculating that Nash equilibrium. So playing a Nash equilibrium is a very strong strategy. Okay. Now, pay attention to this part, okay? If you're off on your phone, just watch this part because this is the key to understanding the next part of this lecture. We are going to improve MiniMax, okay? So we're at the maximizing part of the algorithm. So we're calling the maximizing function. We look, it's not a terminal node yet. So we call the minimizing function. So we look, oh, it is a terminal node now. So what we do is we evaluate it, okay? So this is how it works. It's going depth first search like this. So we found a value of 2, all right? So the minimizing player now knows that the value that it will store will be less than or equal to 2, right? Because it's minimizing. So it sees the next child, and that child has a value of 7. Okay, nothing really interesting happening yet. This is just normal minimizing. So the value of this one is the min of 2 and 7, which is 2. So now the maximizing player knows that the value that will eventually be here will be greater than or equal to 2, right? Because it's going to have 2 here, it's going to have something else over here, but we know that it's going to be at least 2 because we're going to be taking the maximum of both of these things. So it goes down here. It's not a terminal node, so minimizing takes over. It goes down. It says, oh, look, there's a terminal node. So we give it the value of 1, right? We didn't give it a value of 1. It had a value of 1. So now the minimizing player knows that no matter what comes over here, there could be a million extra nodes over here, right? So this could look like this. There could be a million extra nodes over here. But we know, look, that since this node in the search is going to be minimizing over these things, it's going to be 1 or less, okay? But the maximizing node above it knows that it's going to be at least 2. So if we're maximizing between something that is at least 2 and something that is at most 1, we don't even need to evaluate the rest of these nodes. Because no matter what, this node will not have a value that's bigger than 2. Okay? See how that works? So just to go over it one more time, the maximizing player knew that its value is going to be at least 2. But the minimizing player found out immediately that it's going to be at most 1. So even if there's a bunch of 6s or 20s or whatever over here, it's going to ignore them and take the minimum of those. So this can only possibly get worse, right? So if this is less than or equal to 1, then it could never possibly contribute to the maximum value. So we've completely cut off all of the need for all of that computation. So we know that since this is 2, and this is less than or equal to 1, then without ever having even looked at all the possible children that could be over here, that this value is 2. And this process is called AlphaBeta pruning. Okay? The process of using your currently known minimums and currently known maximums in order to chop off parts of the tree for computation. Chopping off parts of a tree, what do you call that? Pruning, right? If you're out in your garden, you're pruning the tree. So we have effectively pruned a part of the tree to save us a ton of calculation, and we have not changed the end result. We are guaranteed to have the same result for less computation, which is absolutely amazing, and we want to do it all the time. So AlphaBeta, this is important. AlphaBeta is not a different algorithm than MiniMax. It is an optimization that is applied to the MiniMax algorithm. So the correct term is MiniMax with AlphaBeta pruning. However, you can shorten that and say, I'm implementing AlphaBeta or the AlphaBeta algorithm, okay? Just know for an exam or for a job interview or whatever, that AlphaBeta technically is an optimization on top of the MiniMax algorithm, but it is commonly referred to as the AlphaBeta algorithm, okay? Or as AlphaBeta search. It maintains all of the properties of MiniMax, but it is strictly better, okay? Cutting off branches of the search tree yields exponential savings. So that's just amazing. You want exponential savings if you can. So AlphaBeta pruning uses the MiniMax algorithm. It introduces 2 new variables, alpha and beta. So alpha is the best alternative for max on this particular passing through the tree. Beta is the best alternative for min on this particular passing through the tree. And the best way that I've found to visualize this is that alpha and beta sort of form this window, and the window gets narrower and narrower as your search goes forward. And you can throw away any results that are outside of this window, okay? Someone in the chat said that they implemented AlphaBeta once, and their search with MiniMax went from 59,000 nodes to 2,000 nodes with AlphaBeta. So there's sort of a rule it's not a rule, it's like a guesstimate for alpha beta. In general, if you searched n nodes with MiniMax, the average works out that with alpha beta pruning, you're going to search about square root of n nodes with alpha beta pruning. Okay, so square root is a huge reduction. It's a huge reduction in the amount of nodes searched for very little extra computation. So if we recall what the max value and min value did, this is the max value and min value algorithms. When we introduce alpha beta pruning, so this is max value and min value just for pure MiniMax, right? We don't have alpha and beta in here yet, but we're going to change these two functions into the alpha beta version of these functions, okay? And here's what happens. We just introduce 2 lines of extra code, okay? So we're going to pass in alpha and beta in addition to the depth. So instead of just state and depth, now we have alpha and beta being passed in. And the extra lines, you can see every line except 2 have changed, okay? So only 8 and 9 have changed. And it's just an extra check to see if that value that we are seeing will never possibly improve our result. Okay, so it says the extra lines just say, so here we're doing our new maximizing check, right? If v prime greater than v, then v equals v prime. The new alpha beta thing says, if v prime is greater than or equal to beta, return v. And this is the check that says, well, this value could never possibly contribute to this minimization, to another minimization, so cut the search off of here, just return. And then we say, if v prime is greater than alpha, alpha equals v prime. Okay, so we're storing the new value of alpha if a cut did not occur. And the opposite thing just happens over here in min value algorithm, where we say, if v prime is less than or equal to alpha, return v. So this could never possibly contribute to a greater maximum, so we don't want to continue on here. And then we record the value of beta. All right, so here we are going to step through a sample running of the alpha beta algorithm on this search tree, okay? So down on the bottom here, this is where we have our terminal nodes, and whatever that may be for whatever game this is, they are just values that we're using for minimizing and maximizing. They don't represent an actual game in any form. When we call max value, okay, so we always call max value first because the first player wants to maximize their choice. So we're going to call max value on the starting state. Alpha is going to be given an initial value of negative infinity, and beta is going to be given a value of positive infinity because beta is going to record the min stuff and alpha is going to record the max stuff, okay? And the depth is going to be 0 for the root node. So that's how we call max value initially. And just keep in mind as we go through this that the values of alpha and beta are passed downward through the tree. So alpha and beta can't help us until we've backtracked a little bit in the search, okay? So here is how alpha beta works. So pay attention to this and you'll know how alpha beta works for your exam or for your assignment, so you can help debug it. So at first, when we first call max value, okay, we are at this node in the search tree. That's the root node. The value is going to be, whenever you see a negative sign here, that means negative infinity. And whenever you see a positive sign, that means positive infinity. So v is negative infinity, because remember up here, this is where we're trying to maximize a value. So the initial value gets negative infinity, alpha gets negative infinity, and beta gets positive infinity. All right. So we look, and this is not a terminal node, okay? So what we do is we call min value. So for min value, the value of v here, which is a new v, okay, it's not the same v as up here. This is its own variable local to this function. since we're trying to minimize here, v gets a value of positive infinity. Alpha gets passed down from the max value calculation. So it's still negative infinity. Beta gets passed down, it's still positive infinity. So no changes there. Then, okay, this is not a terminal node, so we call max value again, and we get those same values. This is not a terminal node, so we call min value again, right? So we're just going down through the tree. But now we are going to finally hit a terminal node. So up here, I have the algorithm, so you can see what's going to happen now to all of these values, okay? This is the min value algorithm. So we're trying to minimize down here, we're trying to choose between these two things, and we're looking at alpha and beta as well. So the first thing we do is we say if the new value is less than our previous best value, then set the previous best value equal to the new value. So is 8 less than positive infinity? It sure is, right? Then it says, is the new value less than or equal to alpha? If it is, then we just return that value. Alpha is negative infinity, and 8 is not less than negative infinity. So that does not evaluate to true. And it says, if v prime, if the new value is less than beta, then beta equals v prime. And that is true, okay? So after that step of the algorithm, v is going to be equal to 8, alpha stays negative infinity, and beta is going to be equal to 8 as well. All right. Then we look at the 7. So we do the same thing. If the new value is less than the previous value, well, we set the new value, or the previous value to the new value. Also, if it's less than beta, we set that value. So after looking at the 7, v is now 7, and beta is equal to 7 as well. And now what we do is we have the values set. We have looked at all the children of this node, so we know now that v is equal to 7. The value of this node is equal to 7, so this is equal to 7, right? And now we can start maximizing over 7 and whatever. But notice that the value of beta that was here 7, that does not propagate back up through the tree, okay? That only goes downward through the tree. So only alpha and beta can only ever help us when we have those values and they're passed down through the tree. We can't propagate those values back up because, well, I'll leave you to figure out why that is, but just know that they only help us when they propagate downward. So now we know that that value is 7, and so now this algorithm kicks in, and it's trying to maximize over 7 and whatever this value is. So here's the max value algorithm. If the new value is greater than v, record it. So v is negative infinity, 7 is bigger than negative infinity, so that will be recorded. If v prime is greater than or equal to beta, return. So beta is positive infinity, so that won't happen. If the new value is greater than alpha, then record alpha. Okay, so it is because alpha is negative infinity. So what we have after this check is that the current best value is 7, alpha is equal to 7, and beta is still positive infinity. But now, so those are the values that we have now. So we're going to pass those values of alpha and beta down into this calling of MiniMax. All right, so now we have a value of, well, initially our value is positive infinity, because remember, we're not passing this value down, we're only passing alpha and beta down. However, we do have alpha and we do have beta. So what is currently happening here? Well, if we look at, let's apply a little bit of mental math outside the algorithm. So up here, this right here, this stage has a value of 7, and it's trying to maximize some stuff, right? So it knows that it will be at least 7. So whatever comes over here on the right-hand side, if that's not at least 7, you don't need to calculate it. And that's what passing down this value of alpha does, okay? It's saying, if the stuff here is not at least 7, don't worry about it. So let's see how that works out. Well, the minimizer down here is looking at a value of 3, right? So it's going to say if v prime is less than v, set the value. So that's going to be true. It says if v prime is less than or equal to alpha, return v. Oh, that's true because alpha is 7 and this is 3. And remember our logic there? This person up, this node up here it knows that it's going to be at least 7, right? But down here, this value is going to be at most 3. So this can, no matter what's here, if it's a 9, if it's an infinity, if it's a negative infinity, will never contribute to this max. So what we do is we just forget about it. We instantly return the value of v, so we know that this is at most 3. So now, up here at this stage, it's saying, okay, well, the new value is 3. It's not bigger than 7, and it's not bigger than positive infinity. So we know now that this value is equal to 7. All right, so that's what alpha and beta are doing. They're keeping track of that window outside of which those values will not contribute to our computation. All right, so let's go back up. Now that we've finished this one, now the minimizer is looking at these values, and it's saying, okay, the new value of 7, is that less than positive infinity? Yes. Is it less than alpha, which is negative infinity? Nope. Is it less than beta, though? Yes. Okay, so now we've got this value for beta that we can pass down through this algorithm. Okay, so here, this stage, well, it's not a terminal node yet, so we'll keep going down. We're passing the value of alpha, beta downward. And now we've finally reached a terminal node. So look at what this is saying. It's saying, is v prime less than v? Yes, it is. Is it less than or equal to alpha? No, it's not. Is it less than beta? No, it's not. Okay, so we've updated the value of v to 9 here. We look at the next one, and we do the same calculation. It's less than v, so we update that value of v. Okay, so now we know that the value of this is 8. The value of this node is 8 because it minimized between these two things, right? All right, so let's look at what this node is now doing. Well, it's saying, I'm going to be maximizing between 8 and something else, right? But the node above it is minimizing between 7 and whatever the value here is. So this node knows that it is going to be less than or equal to 7. However, this node knows it's going to be greater than or equal to 8. And so this is another cut situation. So this is saying if v prime is greater than or equal to beta, return v. So this now knows that it doesn't need to look at any of these nodes, right? It can just cut these nodes off because no matter what, it's going to be returning a value that's at least 8, and the minimizer knows it's only concerned with things that are less than 7. And so we can do another cut there. All right. So now this node has the value of 8 that it returned. 8 is not less than the previously stored value of 7, and so we know that this value is now 7. So now we're back up to the root node, all right? So the root node now knows that this node has a value of 7. So is that better than the previous maximum? Yes, it is. Is it greater than or equal to beta? Nope. Is it greater than alpha? Yes. So we're going to set the value of b and alpha, and then we're going to pass these values down through the tree on the right-hand side. Okay? So let's do that. Well, now we're going down, and we're passing alpha. This is not a terminal node, so we keep going. This is not a terminal node. We keep going. Okay, we're finally at a terminal node. We're going left to right in this depth first search, if you hadn't noticed by now. So here, it's the minimizing node has seen a value of 1. Okay? So is v prime less than v? Yes, because v is positive infinity. Is v prime less than or equal to alpha? Alpha is 7. Yes, so it is. So we can cut off this calculation. Now, this is a deep cut, okay? It's a cut that's like 4 levels deep. And what it's saying is, this is a little bit hard to understand, so I apologize if I mess this up. Intuitively, it's kind of difficult when it's this deep of a cut to see what's happening, but this one knows that is at least 1, right? Or sorry, it's going to be less than or equal to 1, and the value of alpha knows that up here, this is going to need a value of at least 7. So we're cutting it off. I've left out a little bit of that explanation because intuitively it's so difficult to visualize this to just trust the algorithm, okay? So it was less than alpha, so we don't need to look at the value of this. All right, so we know now that this value is 1. So we're going to be maximizing over 1 and whatever this value is. So we keep going down here until we reach a terminal node. And we say, is this less than V? It is. Is it less than alpha? It is. So this is another cut, okay? This is another cut, so we can just return the value of 6. And now we are maximizing between 1 and 6, right? So we set that value equal to 6. So now this node has a value of 6, and I'm stepping through a little bit faster here just because we've done this calculation so many times. Now you can see why these cuts were possible, right? If we look up here at this minimizing node, up here so far, well, the node above it is maximizing, and it needs something that's at least 7, right? That's what this alpha equal to 7 records. So if this is at least 7, and this is minimizing over a 6 and something else, right? Look, V prime is less than or equal to alpha. This is V prime, this is alpha, so we can just cut this whole node of the tree, or this whole branch of the tree off. Because no matter what happens down here, we are going to be minimizing between a 6 and whatever that is, and we're going to be maximizing with a 7 above it, right? So this value will never be greater than 6, so it will never contribute to being greater than or equal to 7. So with that cut, we know that this value is going to be 6 or less. It won't contribute up here, and so the value of the root node is equal to 7. So I know that that may be a little bit complicated to go through on the first pass, okay? But that's just that. And just to let you know, on the midterm, okay, I will not ask you to compute alpha beta values like this, okay? I know that that's a lot to compute. So on the midterm, there will be no alpha beta computation. However, I can guarantee you that you will be given a tree that you have to compute MiniMax for, okay? MiniMax is a far easier algorithm to compute, so you should all get full marks on the MiniMax question. There will not be an alpha beta question, but there will be a MiniMax question, okay? That's just letting you know. Let me rephrase that. There may be a question about alpha beta, but it will not be graphical like this, okay? So understand alpha beta, but you won't have to do like all the alpha beta pruning on the exam, okay? So the computational savings here, in MiniMax, you have the number of search nodes equal to b to the power of d. With alpha beta search, you're approximately cutting the depth in half. Okay, and by dividing the exponent by 2, you are effectively square rooting the number of nodes that you search. And so what that does is you have a depth 7 search with MiniMax becomes a depth 14 search with alpha beta. And so you had a bad program before, and now you have a world champion program. Right? Well, that's a bit of an exaggeration. But being able to search twice as deep, twice the amount of moves into the future, is just, it results in an AI which is much, much, much smarter. Okay? So it's always, you always want to implement alpha beta whenever you're doing MiniMax. Okay. Just give me 1 second. So let's recall the max value and min value that we just did, right? So as we were stepping through this tree, I had these max value and min value. Those were the separate functions. However, just like MiniMax, when we combined these two into a single function, we're going to combine these two into a single function for AlphaBeta as well. So this is the single version, the single function of AlphaBeta, all right? And so what we've done, just like we did for MiniMax, is we took max value and min value, combined them into a single function, where now we just have a Boolean of whether or not we're maximizing, and we just say if we're maximizing, do the maximizing function. Otherwise, if we're minimizing, do the minimizing function. Okay, so that's how we turn max value and min value into the AlphaBeta version of the MiniMax algorithm. However, this is kind of long. Okay, can we shorten it? If you Google AlphaBeta algorithm, you probably will not find this version of the function, right? This is the most verbose possible version of this function. And online, they like to give you their clever versions of the function, right? But this works. It's the exact same result as any algorithm that you'll find online or on Wikipedia or whatever. But can we shorten it? Okay? Yes, I love shortening algorithms. We can do the exact same thing. However, we can get rid of some lines of code. So let's do that. We always want to do that if possible. Here's the max value function, okay? What we're going to do is we're going to reorder the return statement. So this is, I like this. This is telling a story about the MiniMax algorithm, about AlphaBeta pruning. So I'm going through each step of how you're going to shorten this algorithm, okay? So this return statement here, it doesn't matter if that return statement is here or right here, okay? Because the value of alpha doesn't get propagated back upward. So what putting it here is, if it's here, it's a little bit more efficient, because if we do have a cut, we don't need to set the value of alpha. But let's just, for a minute, consider putting it at the end, okay? So we're putting it at the end of the function. All right. Now, by reordering this, what that's done for us is it allows us to compare alpha, which will now store the max of v prime. Okay? So look, this is what this has done. If v prime is greater than alpha, alpha equals v prime. Okay? That's what we set before. However, now alpha has the value of v prime. So we can say if alpha is greater than or equal to beta, instead of saying if v prime is greater or equal to beta. Okay? So by reordering those, we are able to replace v prime with alpha. Okay. So now what that lets us do is alpha is now storing our maximum value. So we can return alpha instead of returning v. Okay? So since we've know that alpha is storing the new max, we can return that instead of v. So v is only now being used as a maximum calculation placeholder. That's all it's ever being used for. See this? So what we can do is we can just completely get rid of v and use alpha as the maximum calculator, right? Because that's what it's storing anyway. If you look through the calculations, alpha is always going to have the value of v or better. So let's just use alpha. So you can see here that v is just storing negative infinity. We're doing the comparison and then we're returning it. But let's just use alpha because it has the same information or better in it. Okay? So what we can do now, look at this. V prime is just a placeholder value as well. So instead of saying v prime equals min value of this, and then if v prime is greater than or alpha, what we really mean is that alpha is equal to the maximum of the previous value of alpha or the call to min value. Right? See how this works? So I've eliminated another line of code. So that's, now we can get rid of the placeholder variable v prime as well. So we can do everything with the alpha variable. And then I can get rid of the blank lines, and now I can look at this. So this is the most compact version of the max value algorithm. You can't get more compact than this, okay? Here, what we can do, there's another thing, is instead of returning alpha here, we can just break, okay? Because if we break out of this loop, what happens? We return alpha. So instead of returning alpha, let's just break, okay? So we break. Fine. It's the exact same effect. It has no difference on the algorithm. However, it will have a cool effect on the following slide. So what we're going to do now that we have shortened the max value algorithm, let's do the exact same thing to the min value algorithm. However, I'm not going to show you all of those derivation steps. I'm just going to put it on the screen. Okay? So I've made these fonts a little bit smaller, but here's what we just did. We just went through max value and shortened it as much as possible. If we went through and applied the exact same logic to the min value function, we would get this. Okay? Really simple. So now we have max value and we have min value. But just watch this. You see over here in the max value, we're saying if alpha is greater than or equal to beta, break. Over here, we're saying if beta is less than or equal to alpha, break. But as you know, comparisons can be reversed, right? Because if beta is less than or equal to alpha, that's the same as saying if alpha is greater than or equal to beta. So, look at this. I'm going to reverse these, and it's the same computation. Cool. Now what we have is, okay, that gives us something pretty cool, because now these statements are the same. All right, so let's look at what we can do with that. Here what we've done, this is the shortened version of AlphaBeta, right? So we shortened max value, we shortened min value. Now we're putting them into the singular version of the AlphaBeta function, right? So we have this variable max. If max, we do that shortened the shortened max value. Otherwise, if it's not max, we're doing the shortened min value function. But look at this. There's duplicate code here. The duplicate code is required due to if max being outside of the loop. But I could move the loop around, right? Because I'm saying if we're maximizing, generate all the children, do something else. Otherwise, if we're minimizing, generate all the children, do something else. But how about I say for all the children, if we're maximizing, do something, right? So here, what I can do is move the for C in children outside. Okay? So now for every child, I can just say, if we're maximizing, alpha equals the maximum of alpha and alpha beta. If we're not maximizing, beta is equal to the minimum. So instead of having the if max on the outside of the child generation, now we have it on the inside of the child generation. But look, this alpha greater than or equal to beta was the same in both loops. So I only need this here now. Okay? And in the return statement, well, here I was returning alpha, right? Here I was returning beta. So for my return statement, I just return, well, if I'm maximizing, I return alpha. Otherwise, I return beta. So I've turned that into one line of code. So this is the final shortened version of AlphaBeta. And it returns the value of the state. The result of this function is exactly the same as the long version. And when you go to implement AlphaBeta, you can implement whichever version you want. And if you go to Wikipedia or you go to like some chess programming website or whatever, this is probably the version of AlphaBeta that you will see. However, if I had just given you this and said, go implement AlphaBeta, I'd be doing you a disservice. Because when I first took an AI course back in like my undergrad, this is what I was given and I didn't understand it at all. How did you get to this from MiniMax? Like, it just doesn't make sense, right? So I wanted to give you all of this derivation because you can understand this, right? This is like the human readable version of the code. And then we went through and showed how we can form an equivalent algorithm which makes less intuitive sense but gives us the same result. Okay? So that's just, I wanted to show you that because you can implement whichever version you want, and in fact, it's way easier to implement the other version because it's way easier to debug the other version. However, here's something really important. Which action do we take? Oh crap. That's what we're really concerned with. We're not really concerned with like what the value is. I don't care about the value. Tell me which action to take, right? So for calculating we're only calculating the value here. But what we really need to do is record the action that gave us the best value. So unfortunately, there's no good way to record the action in the minimized version of the algorithm. So what we need to do is we need to go back to a version of the algorithm that still has this temporary v prime variable. Okay, so let's reuse this temporary variable v for its comparison. All right, and you see here, if max alpha equals max, right? So we've got this temporary placeholder. So let me come here. Here we are calling AlphaBeta within the call to max, but let's just move that outside and store the value, okay? Because the call is the same no matter what. So what we're doing is we're just taking this call to AlphaBeta and we're storing it in a temporary variable. All right, and now we're maximizing this here. And now what I want to do is, this is properly recording the new maximum version for alpha. But what I actually want to do is say, if I have a new maximum, record the action. Okay? So I can't do that if I'm just calling max, if I'm just calling min. So instead of just calling max or calling min, I'm going to say explicitly if I have a new best or if I have a new worst. Okay? So here I'm saying if we're maximizing and this is a new best value, that's what I'm doing here. All right? So if I'm maximizing, that's when I'm concerned with a new best value of an action. It doesn't actually matter which action was taken for a minimizing player. Okay? All I'm concerned with is the action, which action is best for the maximizing player. So what I'm going to do is I'm going to expand this a little bit, and I'm just going to say, instead of having it all on the same line, I'm going to expand it so that I can have one more line. And that new line is just here at line 8. And that says, if the depth of the search is 0, well, what does that mean? If the depth of the search is 0, then I'm at the root node, right? So here in my search tree, the root node, the best action at the root node is the action that I should take in the game. It's the only action that I'm really concerned with, right? So what I'm going to do is I'm going to say that if I'm currently at the root node and I have detected a new best value, then record the best action. So this just says if I'm at the root node, so if the depth is equal to 0, right? Set the best action, this is like a class variable somewhere, equal to the action that generated that child. So you can use a global or a state variable to store the best action at the root node. And so if I take this, which is recording the best action, and I bring it back to the long version of the algorithm, okay, this is what I would have. This is the long version of the algorithm, and if we look back at the other long version of the algorithm, the only change I have here is at line 12, which lets me record the best action at the root node. Okay? Alrighty. So, let's move along. What if we want a time limit? How do I know how long I can search? Right? How do I choose this depth? How is it so maximum? Okay. So, searching to a given depth has variable amount of time. Like if I say search to depth 4, at the beginning of the game, that might take 1 second. In the middle of the game, that might take 100 seconds or a year. I don't know. So the amount of time it takes us to search to a given depth just varies. And so what we're going to do is we're going to incorporate iterative deepening into our AlphaBeta search. And this is called Iterative Deepening AlphaBeta, or IDAB. What is Iterative Deepening AlphaBeta? Well, just like Iterative Deepening Depth First Search, it just says, for each possible depth from 1 up into infinity, perform an AlphaBeta search to depth D. That's it. So, when the time runs out, return the best action from the last fully completed depth. We cannot trust a search that didn't complete. All right. That is very important. If a search did not fully complete yet, we cannot trust its value. Why not? Well, here's why not. Let's say that we are currently searching something, right? So I'm currently searching something here. This is the maximizer. Let's say over here, I've got a value of 3, right? If I haven't fully completed this search, there might be a value over here that's 100. So I can't trust that this is the best move because I haven't seen this one yet, right? I have to complete the search to an entire depth before I can trust the return value of AlphaBeta. Okay, so how in the world AlphaBeta is this is a recursive function, if you hadn't guessed, right? So AlphaBeta is calling itself. So it's a recursive function. How do we escape a recursive function? Well, luckily, we can throw an exception. So this is the sort of trick that all search programmers use to escape searches that are recursive in nature. Just throw an exception. So we can throw an exception when our time limit has been hit and we've escaped, and we use the best value from our last completed search. So rejoice, rejoice, students, because I have given you almost the entire assignment's code in JavaScript for assignment 3. Assignment 2 was a lot of work. Assignment 3 is going to be less work because I'm giving you a lot of the code, okay? A lot of the code in actual JavaScript. So it's going to be less work. Don't worry. So inside our student player, and I'll show you this code when we actually get to the assignment. We are going to have several different class variables on the student or the player student function. So the player student is what's going to have all of your code in it. We are going to have first and foremost the configuration of the search, which is going to take in a time limit, and it's going to take in a maximum depth for the search. We are going to have a variable called current max depth. That's going to be set to 1, and we'll see where that's used later. We're also going to have 2 variables for storing best actions. One is the best overall action that we've seen so far from the most recently fully completed search, and the other one is a temporary variable for storing the current best action in the currently computing search, okay? And we're also going to record which player in the game is the maximizing player. We're also going to have 3 functions. One is called eval. It's going to take in a state and evaluate the state from the point of view of a given player. We're going to have an iterative deepening AlphaBeta function. That's going to take in the state for which we want to evaluate. And we're going to have the AlphaBeta function, which you know what that is by now. Okay. So the iterative deepening AlphaBeta function works like this. And you can almost copy and paste this code into your assignment. Okay. So we're going to set, whenever we call iterative deepening AlphaBeta, we're going to set the best action equal to null because we don't know the best action yet. Okay. we're going to set the maximizing player equal to the current player to move at the given state. So if this was chess, it would be like black player to move or white player to move, right? 0 or 1 in our assignment. Then, for depth equal to 1, up until this.config.maxDepth, d++. So what we're going to do is we're going to loop over all of the different depths from 1 up until our given max depth, and we're going to set this.currentMaxDepth equal to d. So that's a class variable on our search class that records the current maximum depth that we should be searching to. Then we're going to have in a try catch, okay? We're going to try calling AlphaBeta with the state -infinity, positive infinity for alpha and beta, depth 0 to start, and true, we are maximizing, okay? And look at this. This is brilliant. And I didn't come up with this, but it's brilliant. If AlphaBeta, if we hit the time limit inside AlphaBeta, we're going to throw an exception. So, if an exception is thrown, it will skip over this line of code, and we'll catch the exception and break. However, if we didn't time out and we didn't throw an exception, then this line of code will execute, and we will set the best action found so far to the current best action that the current iteration of AlphaBeta had set. So this is how we can tell that our previous iteration of AlphaBeta went to completion or it didn't go to completion, okay? And then, after we've completed all of those depths up until the maximum depth, we return this.bestAction. So what's going to happen here is you're doing iterative deepening on AlphaBeta. You're calling AlphaBeta go up to depth 1, AlphaBeta go up to depth 2, AlphaBeta go up to depth 3. But inside AlphaBeta, it's going to have a time limit, so you're either going to finish the iterative deepening AlphaBeta or you're going to hit the time limit, whichever comes first, okay? And then here is the AlphaBeta function. And I know this might be a little bit small on the recording, apologies, but I wanted to fit it all on one slide. So AlphaBeta, for your assignment, this is the code for your assignment, okay? You have to change this a minimal amount to get your assignment to work. If the state is terminal, or the depth is greater than or equal to the current max depth, return the evaluation of the state with respect to the maximizing player. That's it. So if it's good for the maximizing player, it's a big number. If it's not, it's a small number. Secondly, if the time has elapsed is greater than the time limit, throw a timeout exception. Now, this line of code will not work in JavaScript. You have to set up a little exception class or something like that, but I'm not giving you the whole thing, okay? Then, if it's max, do the max. If it's min, do the min. There is your code for assignment 3. It's done for you, okay? However, here, I am giving you the MiniMax version as well, all right? So, what I recommend for your assignment is to actually go through and implement MiniMax first, get it working with MiniMax first, and then once it's working with MiniMax, go back and introduce the alpha and beta variables, okay? Please do that. It's going to be much easier for you to debug and much easier for you to implement. So just try doing that. Get MiniMax working first, and then go back and do the alpha beta version. And I've just included the short version. If you're a fan of the short version, use the short version. But do not, under any circumstances, implement the short version before you have the long version working, okay? In fact, I would have like alpha beta short and alpha beta long in your code. Like, don't, make sure you always have one working version handy, okay? You don't want to hand in something that doesn't work. Debugging MiniMax can be difficult because it's a recursive function. The values that are returned may not be intuitive from deeper down in the tree. So if you're doing deep searches, the results that you're getting might look like nonsense. So one debugging strategy is to do shallow searches and then print the results that you return. So before I get into this, what I'm going to do is I'm going to show the example. Okay, I'm going to show the examples in the for the actual assignment, because we're going over the assignment now too. I know that we are currently at the time limit, but actually explaining this assignment is not going to take very long, and I wanted to get it all into this one assignment. So let's look at the assignment real quick. Here I've got the code. So here we go. This is assignment 3. All right. So assignment 3 is Connect 4. We are using MiniMax and AlphaBeta to play the game of Connect 4. Connect 4, if you've never played it before, is a game in which you take turns dropping colored discs into the top of this board. So what I've done here is I've simulated the dropping of pieces. So if I click in this row as the yellow player, on the bottom you can see where the piece will go when I move the mouse. Okay? So you stack these pieces up on the bottom, you go back and forth, yellow, red, yellow, red, yellow, red, until someone gets 4 in a row. All right? So boom, look at that. Player 2 wins. So player 1 is yellow, you can see up here. Player 2 is red, and it says player 2 wins because player 2 has placed 4 reds in a row. You can place them horizontally, diagonally, or vertically. So let me just do one more example where I place them in a row. Oh, jeez, I accidentally won with player 2. Let me do that once more. I just want to make sure everything is working. Here we go. There we go. Boom, 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 boom. All right. So player 2 won, and it shows you where that win happened. Okay. So that is the game of Connect 4. It's really, really easy. And the actions in Connect 4 are just going to be integers representing the column number that you dropped your piece in. So this right here, see how I can move across? This, the very leftmost action, is action 0. Place it in column 0. This is action 1, this is action 2, this is action 3, this is action 4, action 5, action 6. So the action in our engine for this game is just going to be the number of the column that you put it in. Now, the only action legality issue for this game is that you cannot put a piece into a column which is full. Okay? So the board can fill up, and if the board fills up, and nobody has won, it's a draw. All right. So that's the only other rule to this game, essentially, is that draws can happen. We can have different sized boards in this. So that's pretty cool. And after you submit the assignment, after they're marked, I'm going to stream an in-class tournament for all the AIs that work properly. Okay? So there will be an in-class tournament. The winner will get some bonus marks and a little trophy. So there will be an in-class tournament in Connect 4 at the end of this. All right. A little bit about the user interface. Up here, you can see that I've included some sample players. Okay? So for example, if we set player 1 to random and we turn on autoplay, then that means player 1, whenever it's yellow's turn to move, I've still got player 2 set to human. Whenever it's player 1's turn to move, it's just going to play a random move. Okay? So it's going to say, there you go. It placed, and it's instantaneous. So just look at where yellow is now. I'm going to place it over here. Yellow placed there. Okay? So it's just making random moves, and I'm just going to make some moves. There you go. If I set both players to random, then I can restart the game, and you can see it just playing games. Just random players playing games. Okay? Cool. I've introduced, I'm going to turn off autoplay now and restart the game. And if autoplay is off, you can hit do single AI turn to do one turn at a time. Okay, so it's a pretty robust algorithm or a pretty robust UI. You can also undo actions. So I can undo actions if I made a mistake. So let's look up here. I've got another one which is called greedy. And what greedy does is it's going to go from left to right, and if it sees a move that can instantaneously win the game, it will. But otherwise, it's just going to go from left to right. So just watch this. Here, let me do that again. So neither player can win, so it's just moving left to right until... So it's red's turn to move right now. So red's going to move here. But now yellow is going to look at all the moves and just take the best move. So yellow, greedy, is the look ahead and evaluate player. It looks ahead and it sees, oh, I can win there, so I'm going to win there. But otherwise, it's pretty dumb. Okay? So if we do like greedy versus random, who's going to win? I don't know. Let's turn on autoplay. Usually, player 1 wins because it's just placing them all in the same row and random doesn't know anything, so that's cool. All right, next we have student AlphaBeta. So student AlphaBeta has 2 parameters. It's going to have a time limit and it's going to have a depth limit. So that's pretty self-explanatory. However, the only additional rule is that if the depth limit is set to 0, you are going to ignore the depth limit. So a depth limit of 0 essentially means a depth limit of infinity. Okay, so in your code, you have to check to see if depth is 0. If it is, you do not do a depth check. Similarly, if the time is 0, you do not do a time check. Okay, so those are the only 2 extra rules, but it's pretty obvious what's happening other than that. All right, so let me show you that. So now, if I set 2 student AlphaBeta players, and I'm going to set their max depth equal to 0 and their time equal to 1 second, that means that your code should do iterative deepening AlphaBeta as deep as you possibly can until 1 second is reached. Now, I have written some solution code that I'm not going to give you, but just to show this. So I have implemented the code straight from the slides. It works in the assignment. If I turn on autoplay here, I have some debug stuff printing out. So you can see here, like I'm making it to depth 5 or 6 here, and my code is essentially running through and doing searches that take 1 second. So every second, it is searching in the... Sorry, it is searching for 1 second and then you see the move happening, okay? So you can see here about once a second a new piece is appearing, so it's working properly. Now, my AI is a little bit dumb because I have not implemented a heuristic function, and we'll talk about the heuristic function in a little bit. All right, so let's pretend for a second that you do not have a heuristic function yet. So that, all right, we'll talk about the evaluation function in a sec. Okay, let's talk about evaluating a board. I think that's a good next place to go. So in your code, there is a function. Let's just open the code. Okay. Player student. Here's the code. Let's go through this. So class player student, you see all the stuff that was in the slides. I don't need to explain that again. The graduate version of this assignment, the only difference is that you have to implement the Zobrist hash function. Okay? I explained how to implement a Zobrist hash function in a previous lecture. The Zobrist hash function is just, that's the grad extra version for this assignment. So I won't go into that in too much detail. So graduate students have to do the Zobrist hash function. Okie dokie. Now, the user interface, the way it interacts with this, with your code, is it calls the getAction function. And all the getAction function does is call your iterative deepening AlphaBeta code. That's it. So that's pretty easy. Here, this is the evaluation function. I'll get back to that in a second, okay? Here is the iterative deepening AlphaBeta function. Currently, it does nothing. So it says this function should implement iterative deepening AlphaBeta. it should call the separate AlphaBeta function which implements the MiniMax search with AlphaBeta pruning. This function should use the this.config configuration options for the following. So we have the time limit and we have the max depth. So a time limit of 0 means that you should ignore the time limit, and a time limit or a max depth of 0 means that there should be no maximum depth. You can ignore the max depth. You can assume that one of time limit or max depth will always be greater than 0. Okay? So please note that both of these limits should be used, and whichever one happens first should be the stopping condition. And the return value of ID AlphaBeta is just the integer action to be performed. And remember that the integer action is just the column of the board. So the ID AlphaBeta function, you just go to my slides, you copy and paste it, and you turn it into JavaScript. Done. Down here, you have AlphaBeta, the AlphaBeta function. This function should implement MiniMax with AlphaBeta pruning. It is recommended that you first get vanilla MiniMax search working properly before implementing AlphaBeta pruning. Please be aware that this function does not return an action. It returns a state value. Actions must be set to a self-class variable rather than just returned. It is also important that you copy states before generating children. Otherwise, you will be modifying a reference to states on different levels of recursion. And I'll explain that a bit more in a second. There is a fun optimization that you can do that doesn't require copying, but I'll leave that to you, okay? So here is the where you put your AlphaBeta code. You go to the slides, you copy it, you paste it in here, and you modify it to actually be JavaScript, okay? That's it. So code for AlphaBeta goes here. Here is the syntax to calculate how much time has elapsed since the search began. You should compare this to this.config.timelimit and throw an error if the time is up. So up here in ID AlphaBeta, I've set this.search start time equal performance.now. And that will return the amount of time that's passed in milliseconds. Okay? So that stores the time in milliseconds in your class. And then in order to get the time elapsed within AlphaBeta, you call the current time minus the start time. That's it. And that whole thing about state copying, in JavaScript, everything is passed by reference. Okay? There's no pass by value in JavaScript. So if you took a state, that's the input to the function, and you did an action, when it recurses back up, that state will be modified, and you don't want that to happen. So inside the GameState class, which I'll show you in a second, I've implemented a copy function. So you always get a copy of the state before doing the action to the child, okay? So the child is equal to the copy, and then you do the action to the child. You never modify the state variable that was passed in. I would set this to const if I could, but JavaScript doesn't allow you to set things to const in an easy way. Okay, and that's it. There's not a huge explanation of this assignment because I've already explained everything and given you the code. So, but quickly, let's look at the functionality for the game state, okay? I have implemented all of the Connect 4 functionality for you, all right? So, the Connect 4 game state has a few different things that you do need to know about. There are several players here. So player is represented, the current player to move is represented by an integer. Player 1, which is the yellow player, is 0. Player 2 is 1. So as you're going back between players in the game, it's player zeros. So zeros, player to turn, or player turn to move, then 1, then 0, then 1, then 0 and 1, then 0 and 1. I've just created these variables for you that you can get access to those. Now you see here that there's player none and player draw. What the hell is player none? Well, the board is going to be represented by a 2D grid. And if we look here, well, there's player 1 is at this location, player 2 is at this location, but these are all blank. And so instead of saying blank, I've called that the none player. So if we look internally, all of the values of the state that don't have a player's piece on it yet just have an integer value of 2. Okay? And there's one other player, which is player draw. And the reason I have that is because there's a function down here, which is check win. Okay? So luckily for you, I've implemented this for you, which is this function is going to return whether or not, oh no, sorry, it's the winner function. So the winner function, which I have already done, it loops through all the pieces on the board, all the rows and columns, and searches for 4 in a row wins in the diagonal, horizontal, or vertical direction. So that's done for you, okay? That function is going to return player 1 if player 1 has won the game, player 2 if player 2 has won the game. If the game isn't over yet, it's going to say player none. And if the game is a draw, then it's going to return player draw. So it's a draw if the whole board is filled. Okay? So that's just how you know using winner. The state copy function constructs an entirely new state and sets all the pieces for you. Okay? So that's what the copy function does. It's similar to Java's clone, but that's what I've done. All right. So if you want to check if a state is terminal, you're going to call the winner function, and a state is terminal if the winner function returns anything except player none. So if it's player none, the game is still going. If it's player 1, 2, or draw, then the game is over. That's how you do that. All right. The check win function is just used by winner, so you don't need to worry about that. Get legal actions goes through each column in the board. Remember how we said that it's not a legal action if a column is full? So here, we would have legal actions for 0 is legal, 1 is legal, 2 is not legal, because this column is full. 3 is legal, 4 is legal, 5 is legal, 6 is legal. So get legal actions would return an array, and that array would contain 0, 1, 3, 4, 5, 6. That would be what get legal actions does. Okay? Is legal action is a function that you can use if you want to. It's currently used by get legal actions. It just returns whether or not the action is an integer between 0 and the size of the board, and whether or not that action, the column is currently full. So that's done for you. It also has do action. So if you say state.do action, it will modify all the internal workings of the board. Okay? So that's already done for you. You don't really need to worry about that. I'm not going to go into the particulars of undo action right now, but it's there for you if you want to look at. And hint, 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 undo action might be the optimization that lets you not have to copy states. Okay? So I'm just going to say this. Get your entire assignment to work with state copying first. And then, and only then. So state copying is very slow. Very, very slow. If you can figure out how to use undo action to avoid the need to copy states, your algorithm will do way better. Okay. So that is what the game state does. It's pretty intuitive. All these variables are pretty intuitive. This dot pieces, that's just the number of pieces on the board. This dot board is the actual 2D array. So this dot pieces is an array of numbers. Right now, array 0 would be 0 because there are 0 pieces in that column. Array 1 would be 1 because there's 1 piece in that column. Array 2 would be 6 because there's 6 pieces in that column. Okay, so that's what the this dot pieces board is. There's also a total pieces variable. That's the total number of pieces on the board. And then this dot board gets you the number of pieces, or sorry, the value of the board. And this board.get xy will return the type of piece at the given xy position. Okay? And I believe that's actually indexed from top to bottom. If it's not, you can figure that out pretty quickly. So if you want to figure out like which piece is where on the board for your heuristic, which we'll get into in a second, you would use, if I go over here to player student, it will be, where's the board? It's in there somewhere. Oh, it's the state, right? So you'd say state, which is the game state, state.getXY, okay? So the only thing that I haven't said yet is the eval function. All right. So the evaluation function is going to be where you spend, hopefully, most of the time on your assignment. Because what you need to do is generate a value for a board that hasn't finished yet. So for example, if I do this, let me do one that doesn't win. Okay. Evaluate this board for me. Give me an integer value for this board, for you. If you are the yellow player, how good is this board for you? How bad is this board for you? Right? This is the value that AlphaBeta is going to use when it does its search. Okay? So, what I've done for you is given you some hints. So, in the evaluation function, I'm going to first get the winner. So, we're going to ask the board, who's the winner? Okay? If the winner is you, the player, I'm going to return some really large value. Just consider this positive infinity. Winning the game is all that matters, right? So this is a really large value. If the winner is the other player, right? So this just says if you're 0, it's 1. If you're 1, it's 0. Then if the winner is the other player, it's negative infinity. It's infinitely bad to lose the game. If the winner is a draw, then it's a 0. Like it's not a win, it's not a loss, it is a neutral evaluation. However, if the winner is player none, it means the game is still going on. So what you have to do is come up with a function that decides how good this game is, right? Because, just watch. Let's say I'm an AI and I'm trying to evaluate stuff. As a human, where would you put your first piece? You'd probably put it in the center somewhere, right? Because what that does is the center, look, at the start of the game, I could make 4 in a row at the bottom. If I put a piece over here, someone could still make a 4 in a row on the bottom, right? But if I put a piece in the middle, nobody can ever make a 4. The other player can never make a 4 in a row on the bottom. So the heuristic function is something. Here's one example of a heuristic function that I like to give. You could say, how many connect 4s are remaining on the board for the other player? How many different ways could the other player still win? Right? If I place my stone here at the beginning, I have eliminated a bunch of ways for the other player to win. So that state has a better evaluation than if I had put the value over here, for example. I won't go into too much detail because I want that to be where you go online, you Google stuff, Connect 4 evaluation, and like really put a bunch of work into that. But the important part being, you basically have negative huge number for a loss, positive huge number for a win, and 0 for a draw. Okay. So the last thing I'll talk about is the tools that I've put into the assignment to help you debugging things. All right? So AlphaBeta can be really tough to debug. So what I've done is I've put in a number of testing scenarios that your algorithm, your AI, should pass in order to get full marks on the assignment. Excuse me. So look at this. Here's a situation. So if I click depth 1 win, this is the first situation. So it's player 1. I've set all of these values up here. So I've set the max depth to 1 and the time limit to 1 second. So with a maximum depth of 1, that means that yellow is going to look at its next move. So it is currently yellow's turn to move, okay? So if this was the human player, I can move anywhere on this board. So let's just go through and see, with just a look ahead of 1, what would my evaluation of every move be? Well, let's just pretend that I have no fancy heuristic function. I just have 0 for a draw, negative infinity for a loss, positive infinity for a win, and 0 for everything else, right? Because I don't have a heuristic evaluation function yet. So if I place my stone here on the leftmost thing, I'm going to get an evaluation of 0 because nobody's won or lost yet. If I place my stone here, I win, right? So I've gotten a positive infinity evaluation. But anywhere else other than here, I will get an evaluation of 0. But here I'll get a huge evaluation of 10,000, for example. So if I just restart and I click that again, this is all set up for me. All I have to do is click Do Single AI Turn. And what should happen is that player 1 should place the stone, if you've done your AI correctly, to take the immediate win. And just look over here in my debugging. In my solution code, I have printed out the values of all of my actions at depth 1. Okay? So action 0, which was over here, had a value of 0. Action 1 had a value of 10,000 because I won the game. So action 2, 3, 4, 5, 6, all of those had an evaluation of 0. So the best action was 10,000 at action 1, so it returned 1 and did that. All right. So that's depth 1. That's only considering moves that I've done. Depth 2. Now this is a depth 2 search, okay? A depth 1 search. So let's look at the situation. What do we have here? It's yellow's turn to move. Yellow has to place a stone here. If we look, red has 3 in a row. So if we do not block red on the next turn by placing a yellow stone here, we will lose. Okay? Let's look at what would happen if we did a depth 1 search. A depth 1 search places the stone over here because all it did was it looked at all the moves that it could do. Just one move that it could do. And none of those moves immediately won the game, so it treated them all equally. But this is where MiniMax starts to be powerful, is when you go beyond that one move and start looking at 2 moves. Okay? So let's look. Let's go back. We click depth 2, block. Now I hit single AI turn. And it placed it in the correct area. The reason was, if we look over here at our depth 2 search, it says, if I place the stone anywhere except action 5, I'm going to have a value of negative 10,000 because negative 10,000 is the value for a loss. So if it places the stone here for yellow and it sees red is going to minimize and red is going to take that win, then it's going to lose. So it recognizes anywhere but right here is going to lose it for me, and so it places it right there. So that's why searching deeper is so important. But it still had a value of 0 for placing it here because it doesn't have a cool evaluation function yet. Let's go one deeper. Depth 3. Okay? Let's evaluate this. Yellow should recognize that in 3 moves, it should win the game no matter what red does, as long as it places a piece in its current line along the bottom row. No matter where red places its piece, it cannot win. Yellow should place its piece in position 2 or 5. A shallower search will not be able to draw the same conclusion. So what this means is, if I set this to human, if I place my stone here or here, right? Look, I've got 3 in a row, and on my next turn, I'll be able to place it here or here and make the win. So if red blocks it here, I win here. If red blocks it here, I win here. So if we go all the way back to this scenario, if yellow plays correctly, it will win the game. However, it cannot play correctly unless it sees at least 3 moves into the future. Okay? So let's run our depth 3 search. Here we go. So over here, our depth 3 search said action 2 is 10,000, action 5 is 10,000, but everything else is 0. Okay? So put it at 2 or 5, and 2 came first, so it put it there. So yellow is now going to win the game. Okay. Depth 4 search is a similar situation. However, it's just one deeper, where yellow should recognize that in 4 moves, it will lose the game if it does not immediately place a piece at either side of red's pieces on the bottom row. If both of the ends are left open, red can place a piece in column 2, then it will win the game on its next move. A shallower search than 4 will not be able to reach that conclusion. Okay? So, that is how you will test your AI. And my AI currently has a max depth of 4. If I do the AI search, it is blocking off red right here. Okay? So your AI should do that as well. Now, everything else, the strength of your AI involves you implementing something clever for this heuristic evaluation function. Because as it stands right now, all it's saying is, do I win the game, do I lose the game, or do I draw the game? Everything else is just 0, so it's just going to keep stacking pieces over on the left-hand side. And if I just show you this, if I set up my current solution to this with just a 1-second time limit, my solution does not have a clever heuristic. So this is what's going to happen. It's going to keep placing pieces on the left, because as you can see, everything is 0, until it can see the end of the game. And once it starts seeing the end of the game, then it starts trying to block people off. There, red saw the end of the game, right? But it doesn't know how to sort of place pieces strategically before it can see the end of the game. So this is what's happening. This is the AI playing against itself. It just keeps going from left to right until eventually player 2 wins. So if we could search infinitely to the end of the game, we wouldn't need a heuristic evaluation. But since we can only search depth maybe 10 into the future for this assignment, we do want to have some heuristic there that says something like, you know what, putting pieces near the middle is probably pretty good. Or blocking off their connect 4s is probably pretty good. So that's all that it is. That's what that heuristic function is. And in order to get full marks in the assignment, you're going to have to implement that. So finally, let's just look really quickly at the marking for this assignment. So we have our obligatory 5 marks for the code style stuff. Your heuristic is worth 10% of your code. Okay, so you have to do something semi-intelligent. You can't just return 0. Iterative deepening AlphaBeta is worth 30% of the assignment. AlphaBeta is worth 50% of the assignment. 6980. We'll talk. Geez, I don't know why I have this in there. The extra part. This should be the Zobrist hash function working correctly. Okay, so that's the extra thing for 6980. And any extra stuff you do for optimizations are open for bonus marks. Okay, so the max assignment mark is 100, and there's the marking scheme for this assignment. And I will be streaming a class tournament, and it'll be really fun. At least it has been in other years. So I apologize for the lecture going over, but once again, I did want to give you as much information on the assignment as possible rather than just releasing the zip file and saying go. Okay, so we're going to go back really quick to the schedule. You're going to have 2 full weeks to do this assignment. You have 14 days until the 26th. It's a ton of time for this assignment. You should be able to bang out this assignment in a night or 2, right? It shouldn't be that bad, but please, please don't leave it until the last minute. It doesn't mean leave it till the last minute. It just means you don't have to work on it tonight, right? It's a lot less coding than assignment 3, or sorry, than assignment 2, and it's going to be pretty fun, I think. And for this case, I will if you want to, and if you can figure out how, you are allowed to trade code with people in the class to battle your AIs against each other to test for the upcoming tournament. However, we are making sure that you don't cheat and copy other people's solutions. Okay? So if you have two friends in another group, you can battle them out if you want. But please hand in your own work and not someone else's work. All right. That's it for today's class. Thank you so much. Remember that we have a midterm coming up on Tuesday on campus. So this upcoming lecture on Thursday. This upcoming lecture on Tuesday, which is technically this Friday, just study for your exam. Okay, I'm not giving you, there's nothing in the next. So because we missed a Tuesday for midterm break, that Tuesday was supposed to be this Friday. There's supposed to be a lecture this Friday. I'm not doing that for this course. Don't worry about anything until the midterm. Okay, well, you could work on your assignment, but just keep going until the midterm. There's a post on D2L about the midterm, the time it is, and the classrooms that you're going to have to come to on campus for that. Please wear a mask. All the COVID restrictions are still in place, and there's no calculators or anything like that. So go read the D2L post. And thank you for sticking it through with this longer one. I know we went for 2 hours, but I just wanted to give you as much information as possible on that. All right. Thank you very much, and have a great evening.